Okay, let us start. So, we saw a proposition in the last lecture which gave us gave us a way to identify the spectrum of a Banach algebra or a star algebra if we know that one element generates it, one element meaning x naught or x naught and x naught inverse or x naught and x naught star. Okay. In that case, you can identify the spectrum of the algebra with the spectrum of the element. Okay. In other words, the Gelfand transform associated with that particular element becomes a homeomorphism. Okay. So, we will use that in the case of the Banach star algebra L1 of Z. Okay. So, let us start. So, back to L1 of Z. We want to find its spectrum, right. So, to find spectrum of L1 of Z, right. So, let us recall some of the things we already know. So, remember we had delta which was delta 0. So, delta 0 was, so L1 of Z consists of all two sided sequences which are summable, right. So, this was I had 1 in the 0th place, right, and then zeros everywhere else, right. So, all the other places it was 0. Okay. So, this was my sequence which was delta and this was the identity. Okay. And define delta k to be, so I should tell you what this is, right. So, delta k n, okay, maybe let me write it here. Okay. So, define delta k by, so I should tell you what is delta k is nth element, right. So, this is 1 if k equal to n, 0 otherwise. Okay. What does that mean? So, you look at 0 0 0 0 and I have 1 at the kth place, right, and 0 0 0 0. K could be positive or negative, right. So, it is like the basis for L1 of Z, right, in some sense. Okay. So, check that. So, this is a property of the convolution which is easy to check, delta j convolved with the delta k equal to delta j plus k. Okay. So, that is how the convolution would look like. Hence, because of this, hence L1 Z is generated by delta 1 and delta inverse, delta minus 1, right, because delta 1 convolved with delta 1 will give me delta 2 and I can get all the delta k's. Similarly, delta minus 1 will give me all the delta minus k's, right, with k negative, and any if I take A in L1 of Z, this is simply in the using the generators, it is just A n delta n, right, n in Z. So, if I get all the delta n's, finite linear combinations of that will be dense, and so the algebra is generated by delta 1 and delta inverse. So, that is something we have seen in the earlier proposition, right. If I have x naught and x naught inverse generating my Banach algebra, then the spectrum is identified with the Gelfand transform of one of those elements, right. By the earlier proposition, sigma of L1 of Z, that is the spectrum of this Banach algebra L1 of Z, can be identified with sigma of the element, right, that is delta 1. So, we just need to find out what is sigma of, so these are homeomorphic, right. So, we will show that sigma of this element delta 1 is the circle T. Okay. So, that is our aim. So, once we show that, that gives us sigma of L1 of Z also, right. Now, we will show this from the first principles, we will just try to invert. So, the spectrum of an element is very easy, right. So, it just lambda e minus x is non-invertible, right. So, we just try to invert lambda E minus x term in L1 of z, and the term the point x is just delta 1, right. So, we will invert. So, we will try to invert, lambda E. So, lambda identity is delta naught, right, which is 1 at 0th place and 0 everywhere else, minus x, right, lambda E minus x, x is my delta 1, right. We want to invert this. Okay. So, if I take a sequence in L1, okay, which is the inverse of this, okay, we have, I want A to be the inverse of lambda delta naught minus lambda delta 1, right. So, if I convolve, I should get the identity, right. So, we have lambda, if A is in L1 of Z such that we have lambda delta naught minus delta 1 convolved with A equal to delta naught, right. This is what we want, right. Then A will be an inverse. So, we will try to solve for A, because we can write down what this is, because convolution is known to us, right. A is a sequence, right. So, A is simply A n, and I want to find out what A n's are, right, how this formula will be true, or for what A n, what A should this be true. Okay. So, let us look at this convolution and look at the nth term of it, delta naught minus delta 1 convolved with A, the nth term of it. Well, this is easy to compute, because both delta naught and delta 1 are very simple, right. So, you can write it down and compute the convolution, or take the convolution inside. Delta naught convolved with A is A, because it is it is the identity, delta naught is the identity. Delta 1 convolved with A will shift A little to the right or left, depending on how you look at it, and you will see that the nth term is simply lambda A n minus A n minus 1. Okay. So, the convolution is given to us, and I want this to be identity. So, if this is identity, only the 0th term should survive, 0th term should be 1 and all the other terms should be 0, right. Okay. So, let us see. So, hence lambda delta naught minus delta 1 convolved with A is equal to identity if and only if lambda A 0 minus A minus 1 equal to 1, right. So, that is the n equal to 0 term, right. When n equal to 0, I get lambda A 0 minus A minus 1, and at 0th place I want it to be 1, and everywhere else it is 0, right. So, lambda A n minus A n minus 1 should be 0. So, that is A n minus 1 when n is not 0, right. So, that is how we want. Now, we solve for A, right. So, I want to find if there is an inverse or not, right. So, solve for A, so or solve for A n, the nth term, by recursively. So, recursively, let us see, A minus 1 is 1 lambda naught. So, let me write it properly. From here, A minus 1 equal to minus 1 lambda A naught. So, A naught you choose arbitrarily, and then you solve for A 1, A 2, A 3 and A minus 1, A minus 2, A minus 3 and so on. So, the first one gives me A minus 1, the other ones give me. So, if you look at it very carefully, you will see that A n is equal to lambda to the minus 1 A 0 if n is greater than or equal to 1, right, lambda A n equal to A n minus 1. So, each time you do, you get a lambda, right. So, that is why lambda to the minus n. Similarly, lambda to the n minus 1 into A minus 1 if n is greater than or equal to 1, okay, or the other way, n is less than or equal to 1. So, I should n less than or equal to okay. So, let me rewrite this, so that this is okay. So, maybe this is not the correct way to write, and A minus 1 equal to lambda to the n minus 1 a minus 1 for n greater than or equal to 1. Okay. So, that tells me everything about all the coefficients in the sequence A, right. So, this is just recursive relationship and then you solve it. Okay. So, there is nothing there. Problem is we do not know if ANs are the ANs are summable, right, because this solution we have found A should be in L1, right. So, but summation mod AN is finite implies, well, what will happen? Look at these terms. Okay. So, when I add A naught is something which comes out and I have just summation mod lambda to the minus n, and in one case I have mod lambda to the n. Okay. So, if you look at it, you will see that A naught has to be 0 if mod lambda less than or equal to 1, right, because I have lambda to the minus n here and it will blow up, right, and A minus 1 equal to 0 if mod lambda is greater than or equal to 1, right, because here the lambda to the n minus 1 will blow up. So, if A minus 1 is non-zero, you can't have an L1 sequence, right, a summable sequence. Okay. So, hence, so this already tells me that when mod lambda equal to 1 there is no solution. Okay. Hence, if mod lambda is not equal to 1, we get A equal to minus summation n equal to 1 to infinity lambda to the n minus 1 delta to the minus n if mod lambda is less than 1. So, that the series converges. So, one side will become 0, the other side survives and you will get this, and similarly summation n equal to 0 to infinity lambda to the minus n minus 1 delta to the n if mod lambda is greater than 1, right. In both cases the series will converge, they are in L1 because delta does not do anything, I have just lambda to the some power, right. If mod lambda is greater than 1, that series converges, similarly for the other one. So, whenever mod lambda is not equal to 1, I have an inverse, right, and there is no solution for mod lambda equal to 1, right, because once mod lambda equal to 1 and you have just A zeros and A minus 1s, right, and so it will not converge, right. So, both will have to be 0 and you will get 0, right. Clearly no solutions for mod lambda equal to 1, okay, which is same as saying hence sigma of this element delta 1 is the circle, right, because for any lambda outside the circle we have a solution. Okay. So, that identifies the spectrum of L1 of z. So, this is also going to be equal to spectrum of L1 z, right, the algebra L1 z. Okay. Now, we still have to do the Gelfand transform. So, we have only identified it as a set, right, sigma of L1 of z, that means all multiplicative linear functional. So, I take any element in the circle, there is a multiplicative linear functional associated with it, right. So, let us find out that. Okay. For each e to the I theta in T, so that is the circle and that is also the spectrum of delta 1, right. So, spectrum of an element is the range of the Gelfand transform, that means there is a multiplicative linear functional phi which will take delta 1 to this particular e to the I theta, right. So, there exists phi, of course, phi will depend on theta, right. So, when I change e to the I theta I will get another phi. So, let me put a phi theta there just to say that it depends on theta, phi theta in sigma of L1 of z, right, a multiplicative linear functional such that phi theta at this point delta 1 is equal to e to the I theta, that particular value in the spectrum, right. So, lambda in the spectrum is taken, right, phi of x equal to lambda. Now, let us find out how phi theta acts. So, phi theta takes delta 1 to e to the I theta. So, where will it take delta 2? Well, delta 2 will go to e to the I 2 theta, right, because delta 2 is delta 1 convolved with delta 1, phi theta is multiplicative. So, it will go to e to the I 2 theta. So, delta n is delta 1 convolved with delta 1 convolved with n times and multiplicativity will take it to e to the I n theta. Okay. So, if A is in L 1 of z, okay, so A equal to A n, then we can write A as summation A n delta n, right, n in z, okay, and that converges in the Banach algebra, right, because it converges in the norm. Now, because phi theta is continuous, by continuity of phi theta of A, right, that is what we want to find out what exactly it is summation, it is an infinite sum, but it converges in the norm. So, the phi theta can go inside A n phi theta of delta n, right, and this you can check that is equal to e to the I n theta as I said earlier, right, and that is the Gelfand transform, right. So, phi theta at A is this, and so if I take A and I look at the Gelfand transform, that is acting on the spectrum. Spectrum is identified with the circle, and if I look at one multiplicative linear functional given by theta, that is simply summation A n e to the n theta, right. So, these are the absolute summable Fourier series, right, summation mod A n is finite. So, these Fourier series as a function of theta are absolutely summable. Okay. Now, a corollary to this is a rather famous theorem due to Norbert Wiener about absolutely summable Fourier series. Okay. So, let me write down corollary. Okay. So, corollary is a theorem due to Wiener. Okay. So, if f of e to the I theta is equal to summation a n e to the I n theta n in z. So, I am taking a function on the circle group and expanding it in terms of e to the I n theta. Okay. So, this is something you would have seen in basic function analysis, that e to the I n theta is an orthonormal basis for L 2 of the circle, and L 2 functions can be expanded in terms of e to the I n theta, which is a which converges in L 2, right, but here I am taking a function whose Fourier series converges absolutely. Okay. So, with summation mod A n is finite. Okay. So, I have absolutely summable Fourier series. Suppose f never vanishes. Okay. So, that is an important condition, that means f is never 0 on the circle. Then of course, 1 by f makes sense, right. 1 by f is a nice function, because f is continuous, right, because it is absolutely summable, and so it is going to be a continuous function and it is never 0 on the circle. So, 1 by f is another continuous function on the circle. So, it has a Fourier series, right. So, I can write this as summation b n e to the I n theta, right. This much is of course trivial, there is nothing here. The theorem of Wiener, which is quite famous, is that 1 by f also has a absolutely summable Fourier series. So, then 1 by f is summation b n e to the I n theta with summation mod b n to be finite. Okay. So, this is a rather strong result, that if I have, because there is computing the Fourier coefficients of 1 by f is not going to be very easy. Okay. And Wiener's theorem says that if f has absolutely summable Fourier series and f never vanishes, 1 by f also has the same property. Okay. Well, how do you prove this? So, we will use Gelfand theory to prove this, and your proof is just one line. Okay. So, this was quite an achievement. Proof. So, we have seen how the Gelfand transform on L 1 z looks like, right. If I take a sequence A, which is just a n, two sided sequence which is summable, then the Gelfand transform is the summation a n e to the I n theta, which is the Fourier series of the function, right. So, we use whatever we know from the Gelfand theory to prove this. Okay. So, given that f equal to a hat, right. So, if I start with f to be equal to summation a n e to the I n theta with summation mod a n finite, then in the Gelfand transform language my function f at e to the I theta is a hat at the multiplicative linear functional which is given by phi theta, right. So, f is a hat where a is envelope of z, and we are saying that a hat never vanishes, right, and assumption is that a hat never vanishes. Okay, which means remember what is the spectrum of A? The spectrum of A is precisely the range of the Gelfand transform, and we are saying Gelfand transform never vanishes. Okay. Hence, 0 is not in the spectrum of A, right. So, 0 is not in the spectrum of A is same as saying A is invertible. A is invertible, right. So, there exists B in A which is L1 of Z here such that A star B equal to identity is delta naught, right, because we are in L1. Okay. So, but one should take the Gelfand transform, hence A hat times B hat equal to 1, right. Gelfand transform is multiplicative, right, it is a multiplicative algebra homomorphism. The algebra product on L1 is the convolution. So, when I take the Gelfand transform, it has to go to the product, right, product pointwise product on the other side which is continuous functions on the spectrum, right. Okay. So, hence A hat B hat is equal to 1. So, B comes from L1 of Z, right, and 1 by f is simply B hat, right. So, that is all. So, I have the Fourier coefficients of 1 by f to be B, and B is absolutely summable, that means it is in L1. So, I have this never vanishing absolutely summable Fourier series, then its reciprocal is also absolutely summable. Okay. Okay, so, the proof you can see is very easy. It is it was a quite a tough theorem due to Wiener in the beginning, but once Gelfand developed this theory, this became very easy. Okay. Now, let us look at, so just a comment on L1 again. Note that we will do one more example. Okay. So, note that L1 of Z is a Banach star algebra, by, so A star is defined to be A minus n bar. Okay. And L1 is symmetric. So, you can check that L1 is symmetric, that is very easy, check that L1 is symmetric. Okay. Well, we can check this directly now. So, A star, so I want to know if A star hat will go to A hat bar, right. So, A star hat at e to the I theta, remember the spectrum is just a circle, this we know is summation n in z, A star the nth element e to the I n theta, right. That is how the Gelfand transform is defined, but this is n in z. A star is defined to be A minus n bar e to the I n theta, right. So, e to the I n theta you can write as n in z A minus n e to the minus I n theta and whole bar, right. But whatever is below the bar is precisely the Gelfand transform of A, right. So, the star goes to the complex conjugate of a hat, right. So, that means it is symmetric. Okay. One can also define the involution to be A star n to be just A n bar instead of taking A minus 1. Okay. But L1 is not symmetric. So, this is easy to check, but L1 is not symmetric, with respect to this involution, Okay. and of course, L1 is also not a C star algebra. Okay. So, exercise L1 of Z is not a C star algebra with respect to the involution A. So, the first one, the A which makes it to, because C star algebra has to be symmetric, right. So, here is a symmetric commutative Banach algebra with identity which is not a C star algebra. So, A star n equal to A minus n bar. Okay. So, you find two elements, so that the C star algebra identity is not true, right, x star x equal to norm x star x equal to norm x square. Okay. So, let us look at one more example. L1 of the real line. Okay. So, if you remember, here we had defined the Fourier transform which was the multiplicative linear functional, and we will show that these are all. Okay. So, I will give this as an exercise with some steps. Okay. So, if phi is in the spectrum of L1 of R, then there exists T naught in R such that the corresponding. So, I am identifying all the multiplicative linear functionals with points on the real line, and that point gives me a multiplicative linear functional. Okay. So, such that there exists T naught in R such that phi at f equal to, so I will denote it by phi sub T naught f equal to integral over R f of x e to the I t x naught dx, right. So, f is my function in L1 in the Banach algebra with respect to convolution, remember that, not point-wise product. It is a Banach algebra with respect to convolution, and multiplicative linear functionals are precisely the Fourier transform evaluated at points. Okay. So, this integral is called the Fourier transform of f. Well, how does one prove this? So, this is only steps. One is it is a linear functional, right. So, phi of f is given by integral over R f of x beta x dx for some beta in L infinity, right. That is how your linear functional will look like. Okay. I want to find out beta and say that it is actually exponential, right, e to the I t x naught and what not. So, what do I know? This is the multiplicative linear functional, right. So, we have phi of f star g equal to phi f phi g, right, because the phi is a multiplicative linear function, right. Apart from being linear, it is multiplicative. So, let us write down this identity. What is f star g? That is f of x minus y g y dy, right. This is my f star g at x, and I have to integrate this with respect to beta, right. So, beta x dx. This is equal to, well, integral over R f of x beta x dx. So, that is phi of f times integral over R g of y beta y dy. So, I write x and y so that it is easy to identify what is happening. So, I can write both as double integrals using Fubini's theorem. So, let me write one more step, f of x minus y g y beta x dx dy equal to integral over R integral over R. So, I combine these two, I have f of x g of y beta x beta y dx dy. Okay. So, here f of x minus y I change to f of x. So, this will look like integral over R integral over R. So, change x to x plus y, and Lebesgue measure is translation invariant. So, this simply becomes f of x g of y, x becomes x plus y. So, it becomes beta of x plus y dx dy. right. So, these two are equal and these two are equal. So, now you see you have f of x and g y here, f of x and g y here, conclude that. So, there is still some work to do here, these are bounded functions, right. So, conclude that beta of x plus y equal to beta x beta y, okay, almost everywhere and so on. So, there are always measure theoretic things involved. Okay. Now, if you look at this again, I have g y dy here and I have g y dy here. Okay. So, if I look at that a bit more carefully, I see that. So, let's take one more page. Okay. So, let me write down that part. So, I have integral over r f of x minus y g y beta x dx dy equal to integral over r. So, let me write g y dy outside and I have integral over r f of x beta x times beta y, right. There is a dx here. Okay. Let me dx beta y dy dy. Okay. So, you look at g y dy here and see that I have g y dy here. So, this should give me. So, again this is something you have to check, integral over r f of x minus y beta x dx equal to integral over r f of x beta x dx into beta y. Okay. Again almost everywhere. Okay. But this tells me that, so the left hand side LHS is continuous in y. It is a convolution, right. So, it is a convolution of L1 function with an L infinity function. So, it is continuous. So, this tells me beta is continuous. Okay. So, you choose an f, so that f is continuous, say compactly supported, you will see the left hand side is continuous and you choose f such that the right hand side is non-zero, right. So, that can be always done. So, beta is continuous and I have beta x plus y equal to beta x beta y. So, what we have is beta is continuous and beta x plus y equal to beta x beta y. Now, you can assume this to be for every x and y, right, because it is continuous. Okay. It implies that beta is a exponential, beta is e to the ax, but beta is in L infinity. So, it is a bounded function. So, beta x will have to be equal to e to the I t naught x for some t naught. Okay. So, what we have proved is any multiplicative linear functional on the Banach algebra L1 of R is given by integration against an e to the I t naught x. Okay. So, consequently we have sigma of L1 of R identified with R itself. Okay. Of course, there is still we did not say anything about the topology, but that part is more or less clear and easy to prove that this is a homeomorphism, that any if I take a multiplicative linear function, there is a t naught, and if I take an element t naught in the real line, there is a multiplicative linear function, that is a 1 on 2 map and it is continuous and its inverse is continuous. You see now this is a non-compact space, right. The spectrum is non-compact because the Banach algebra does not have identity. Okay. We will see that a little bit more in the next lecture. Okay. So, we will stop here. In the next lecture, we will look at the Gelfand-Naimark theorem for C-star algebras. So, as I said, C-star algebras are quite nice. We will see that the Gelfand transform is an isometric isomorphism, thus identifying the C-star algebra with continuous functions on a compact Hausdorff space. Okay. So, that is what we will do in the next lecture. Okay, so we will stop here.